Hello everyone, I am Onat. I am a third-year PhD candidate at University of California, San Diego and San Diego State University. Today, I am going to present our paper, CAHEROS, Constraint-Aware Heuristic Approach for Robust Sensor Placement. So, as a solution for robust sensor placement, we have three different approaches. So the first one is exhaustive search, where we enumerate all possible solutions and select the best one. So as you might imagine, this has a huge complexity, exponential complexity, which is only suitable for very small problem instances. In optimization, we construct mathematical models, specifically integer programming models, which can be easily solved by conventional solvers. So the problem of optimization is it is NP complete, meaning that the problem may become intractable for large or very large problem instances. As an alternative to optimization, in order to obtain quick solutions, we have heuristics, where we can find nearly optimal solutions. So this is tractable even for extremely large problem instances, and we obtain the solution really quickly. So our contributions in this paper, the first contribution is to construct integer linear programming formulation for robust sensor placement problem. Then to solve this problem for large problem instances, we propose constraint-aware heuristic approach, where we adapt 4 different heuristic methods. To show the validity of our proposed approach, we use a sheet metal shop floor layout testbed, and the figures indicate this layout. Our goal is to go from ILP to constraint-aware heuristics. So let's start with the mathematical formulation or mathematical optimization model, which you are already familiar with. So here are the decision variables and the inputs. So we call this model coverage only, where our objective is to maximize the number of point of interest detected, where the first constraint ensures that each point of interest can be detected by a certain amount of probability, and the second constraint ensures that we place exactly n number of sensors. So in order to add robustness to this coverage-only method, we first define a metric, which we call detectability degree, that measures the total detection probability of all point of interest G. So based on this robustness metric, we calculate the average and minimum detectability degrees, and we also take the distance between sensor and point of interest into account by separating the distance into nominal distance and largest dispersion. So here are robust optimization formulation. So here we maximize the weighted sum of average and a minimum detectability degrees, where our first constraint ensures that each point of interest can be detected by a certain amount of probability, whatever the distance between sensor and point of interest. So this is the robust optimization addition that we go from coverage only to robust. The second constraint comes from above, which ensures that we place exactly n number of sensors. So what is constraint handling heuristic? So normally heuristics do not consider the constraints of an optimization problem. Yet there are many methods to consider to take constraints into account. So penalty method is one of them, where we convert a constraint problem into its unconstrained version by adding constraints to the objective function. So let's consider a simple mathematical optimization problem where we have only one constraint, inequality constraint. So we can write a new objective function as follows, where psi x is nothing but the difference between our objective minus px, where we define px as the summation of theta g times maximum of 0 and fgx squared over all point of interest, over all g's. So here theta g indicates the penalty factor, which is a non-negative number. So as you can see, if we do not violate the inequality constraint, this px comes out as 0. Whereas if we violate, then we multiply this with a penalty factor and we sum over all possible point of interest or over all G's. So as you might remember, we had these constraints. So the first constraint can easily be implemented within heuristic. Okay, at each step, we can tell heuristic to place exactly n number of sensors. That is why we are fine with this constraint. What about the second constraint? So we need to use this penalty method since it is hard to tell our heuristics to implement at each iteration. So what we do here is we write the above constraint in FGX format, and then we know already that f0x, which is nothing but our objective function of our robust optimization model, and we select theta g as 10 to the 14 for all point of interest for all g's. So what we are going to do at each iteration, we compare penalty-induced objective value psi x to update the best solution. So we select different robusturistic methods. And so the contribution of ours is to add robustness to these heuristic methods. So at each step, we calculate this psi x and we update best sensor placement scenario found so far if we improve this value, if we improve the psi x value. So overall we select 4 different heuristics. Grid algorithm, I think this is one of the well-known heuristics in the literature. So it selects local optima at each step, at each iteration, to eventually obtain a global optimal solution. So and the second one is simulated annealing, which is based on a cooling process of a material. It tries to avoid from local optima by changing the temperature dynamically. Whale optimization algorithm is comparatively newer one, which is based on the special hunting behavior of humpback whales. It follows exploration steps. And randomized algorithm is our baseline algorithm for comparison purposes, where basically we select random locations for sensor placement. Experimentally, we first measure the performance of selected heuristics, where we place different number of sensors and calculate our robust optimization model objective function. So here on the x-axis, we have the number of sensors, and on the y-axis, we have the objective value, and each color represents different heuristic methods selected. So as we can see, grid algorithm always performs best at any sensor placement configuration. Statistically, RGA improves the system robustness by up to 18% compared to our baseline robust randomized algorithm. And as expected, simulated annealing whale optimization algorithm and grid algorithm can outperform randomized algorithm. So as a summary from this slide, when we compare heuristic robustness performance, RGA is the best, followed by whale optimization algorithm, simulated annealing, and robust randomized algorithm. We also looked at the computational overhead of selected heuristics, where we measured the execution time of the heuristics. So here is the outcome for this experimental analysis. Again, on the x-axis, we have the number of sensors. On the y-axis, we have the execution time. So here we observe that a grid algorithm becomes the slowest algorithm as we increase the number of sensors. So from that, we can conclude that there's a trade-off between execution time and performance. Remember that grid algorithm was the best, but it is the slowest algorithm when we increase the number of sensors. Statistically, so as an example for that trade-off, grid algorithm is 12% better than the whale optimization algorithm, while it needs 150% more execution time at 100 sensors. We also compare heuristics with the optimal solution. So where we conclude that grid algorithm can find a solution 400 times faster than conventional solvers, which corresponds to the solution of the optimization problem, while only being 5.5% less optimal. This is a really great conclusion, Although we are not far from the optimal solution, we can obtain much faster solution. Lastly, we also implement the heuristics based on only considering the number of points detected, maximizing the number of points detected. So when we do so, here each subfigure represents different heuristics, and RA, for instance, on the left top one, we have RA represents coverage only version of randomized algorithm, and we have also robust version. So we can see that robust versions of these heuristics always provide better robustness level. So here objective value represents our robust model objective value. So statistically, our robusturistic methods increase the system robustness by up to 48% compared to coverage-only approach. So as a conclusion, robust sensor placement is essential. It's critical to deal with the possible sensor breakdowns and probabilistic sensor detection. So for that purpose, we first share our robust mathematical optimization model. And then in order to solve this problem for large instances, we adapt a variety of constraint-aware heuristics. And we showed that grid algorithm is providing us the highest robustness level. However, it requires high computational overhead. Systematically, heuristics can increase the system robustness by up to 48% compared to a coverage-only version of these heuristics. When we compare this to optimal solution, we can find 400 times faster solution than conventional solvers, while only being far from 5.5% from the optimal solution. Okay, thank you so much for listening.